Hi Internet, it's Tori. I'm coming to you today from my office. As many of you know, I'm a magician, but turns out I'm also pretty good at math. I even have a PhD and everything. See? Anyway, today I want to do a demonstration of 8 perfect Faro shuffles, and I'll describe what I mean by that in a moment, but it's a well-known fact amongst magicians that if you perform a perfect Faro shuffle, and this is where you weave the cards perfectly one and one, if you do this 8 times, you'll return back to the original order. And this is actually a really interesting mathematical fact that I wanted to talk about in a little bit of detail and then demonstrate. So before we do anything else, let's go ahead and start with some definitions. A permutation on n objects is a specific rule about how to rearrange the order of those objects. So this is something we do in everyday life a lot, but we want to formalize this idea so that we can explore its features. For example, this little loopy arrow diagram describes a permutation on 3 objects. It's telling us take the object in position 1 and move it to position 2, take the thing in position 2, move it to position 3, take the one in position 3 and move it to position 1. So I've drawn up this little chart so I can demonstrate the effect of this permutation on a collection of 3 objects. I've just labeled them A, B, and C so that we can keep track of them. So if I follow the rules here, the thing in position 1 goes to 2, 2 goes to 3, and then 3 goes to 1. So this is an example of an iteration of this permutation. I've applied it to this collection of objects one time. So a natural question to ask is, well, if I keep doing this, is there a way to get back to the original order? And you can see pretty quickly that there will be. If we even just look at the this sort of representation here, if you keep going, if you move 1 to here, and then to here, and then back, it only takes 3 times for it to return to its original spot, and that's true of both 2 and 3 as well. And we can demonstrate that with this actual sort of tangible example just by performing the rules again. So 1 goes to 2, 2 goes to 3, and 3 goes to 1, and then one more time gives us our original order again. At this stage, it's going to be advantageous to introduce a little bit of notation. Instead of writing this long, loopy diagram every time we want to describe one of these permutations, we just use the numbers in order in parentheses. So this is still telling us that each number, the object in that position goes to the thing that comes after it. When you get to the end, you just loop back around. And such a permutation is what we call a cycle. We define the order of a cycle to be the number of things in it. So in our previous example, that cycle had order 3. And it turns out that this is exactly equal to the number of iterations it takes to return the objects to their original configuration. So our next question is, what happens to the order if we have a permutation that's described as a combination of a few cycles? So we'll kind of demonstrate with this example where I have the cycle moving the first 3 elements in order, 1 to 2, 2 to 3, 3 to 1. That's the same example we had before. And then the 4th and 5th element, 4 to 5 and 5 to 4. So notice this 2-element cycle is just switching these 2 elements. So if we execute this permutation, we start the first step with something like this. Okay, and then we can just keep going. And after 3 steps of this permutation, we knew from our previous exploration that this guy has order 3. And that is indeed reflected by the fact that after we execute this permutation 3 times, we do get back the original ordering for this part. But this part is not in the original ordering. Okay, we've switched it. So we see that in order for this part to return back to its original, we have to have an even number of iterations. We have to have done this an even number of times. So we start it off again, or keep it going. It's going to start this part again. We'll get something like this, and keep going. Oops, running out of room. With one more, we should get back to our original ordering. So the observation is that the order of this permutation as a whole, it had to be a multiple of the order of each cycle, because in order to get the pieces affected by that cycle back to their original thing, it has to be the order of the cycle or a multiple of it. If it's a multiple of it, you're just going through the whole thing again, as we saw happened in both cases. With the 3 cycle here, we had to do it twice, or with the 2 cycle, we had to do it 3 times. We have the following facts about permutations on n objects. The first one is that any permutation on n objects, so any way to describe rearranging those objects, has a unique what we call cycle decomposition, or representation as a bunch of cycles. And then the second fact is that the order of our permutation is just going to be the least common multiple of the orders of all the cycles. So if we can represent a permutation in terms of cycles, then we can find out how many times we need to apply that permutation to return to the original ordering of the objects. So now that we've developed some of the combinatorial tools necessary to approach this problem, we see that we've reduced the question of how many perfect Faros does it take to get back to the original order of the deck to expressing the permutation of executing a perfect Faro in terms of cycles. And if the lowest common multiple of the order of each of those cycles is 8, then we know that as a permutation that perfect Faros have order 8. So I've been talking a lot about perfect Faros. I'd like to actually demonstrate one now. So the idea is that you take your pack of cards and divide it into 2 equal packets of 26 each. Like you would for a riffle shuffle, the idea is that we're going to weave these together, but we're going to do so in such a way that they're exactly alternating from the top and the bottom. So that's something like this. Okay, so you can see that we've got this nice alternation. So we need to be a little bit careful. There's a few different ways we could do this. Notice I took this packet from the bottom, so my original ordering was this, with the Ace of Spades on the bottom and the Ace of Hearts on the top. So what I'm going to require in my perfect Faros is that the bottom card, or the card in what we'll call position 1, stay on the bottom. All right, so in order to better understand what's going on, I created this small example with just 8 cards. So what this is describing is that I color-coded it for the black means the bottom half of the deck, and the red means the top half of the deck. So remember, we specified that we want to Faro our cards in such a way that the bottom card stays on the bottom. So this is like that Ace of Spades, and we'll call it position 1, stays in position 1 when we execute this permutation. And then after that, the idea is that we have this top half now, and we want to weave those alternating with the existing bottom half, which will stay in the same relative order, as will the top half. Okay, so what we want is kind of a general formula describing the new positions, right? So we can, let's examine each half separately, because they're going to follow different rules. So let's start with the bottom half. All right, so let's say we want to know about position K, and we want a formula for what K's new position is going to be. So in this case, K is 3, and its new position is 1, 2, 3, 4, 5. So what we want is a general rule that will work for all of these, and ultimately for all 52 cards in the full deck. All right, so let's take a look at what's going on here. The way we can think about this is that if this card is in position K, then there are K minus 1 things that are before it. Okay? So after we do the shuffle, that number is going to double. The number of things before the new position is going to be 2 times K minus 1, because we put a new card behind each of those. Okay, but the position of our card, this is going to describe this position. We need 1 more, so we get plus 1 for this guy. All right, so the general form that is going to tell us if we started if we're on the bottom half of the deck and we're in position number K, whatever K is going to go to, it's going to be 2 times K minus 1 plus 1, which simplifies to 2K minus 1. All right, and you can check that that works in this example, and later on we'll see an example with the whole deck. But just that, so like card 1 starts in position 1, 2 times 1 minus 1 is 1, so that holds. Card 2, well, 2 times 2 is 4 minus 1 is 3, and that's in position 1, 2, 3. So you can check 4 if you'd like. But this reasoning should hold in general. So now let's examine what happens with the top half. So here's how you can think of that. Let's look at another card. I'm going to call it J, so we don't mix up our calculations. And we'll say, okay, well, J is some position, and it's going to be greater than half the deck. So in this case, it's going to be greater than 4. So if I wanted to just look at the relative position in this half of the deck, once I've split them off, that's going to be, we're going to get that by J minus n over 2, where n is the total number of cards. In this case, n is going to be equal to 8, number of cards. Okay, so that's going to be the relative position of J. Okay, and then to get the new position of J, well, the relative position of J is here. Well, what happens? How many other cards are there? Well, it's just going to double, because in front of each of those cards on this packet, you've put in another card. So the total thing is going to be 2 times this. Just because for this relativized position, like if it's in position 3 relative to just the top half, then once we complete the Faro, it's going to be in position 6 because we've added a new card for every single position. So from that, we get this is equal to 2j minus n, because these 2's cancel. So j is going to map to 2j minus n. So in a deck with n cards, we can summarize this information as follows. If you start with position k, if k is in the first half of the deck, which can be expressed by saying that k is less than or equal to n over 2, then k will get mapped to position 2k minus 1. And if k is at the top half of the deck, in other words, k is greater than n over 2, then the new position of k will be 2k minus n. I went ahead and rewrote this with n equals 52 plugged in, since we're interested in Faros of 52 cards in a whole deck. So that gives us this following rule. Now remember, our goal was to represent this permutation in terms of cycles. So we're not there yet, but this is going to give us a tool in order to determine what the cycles are going to look like. Okay, so here's how we can use this information. So for example, let's start with seeing what 1 is going to do. Now, we kind of know this one. We actually talked a lot about it. The first position, or that ace of spades, we want it to remain fixed, right? So the only place it should ever go is back to 1, or itself. But we can check that that coincides with this rule, which it will. 2 times 1 is 2, minus 1 is 1. So in this cycle, that's it. That 1 is going to be alone. And this is what we call a cycle of order 1, or this corresponds to what we call a fixed point in the permutation. Just that that 1 is never going to get mapped anywhere else, that card is always going to be in that position. And we actually have one other fixed point in this permutation, which is the top card. And you can think about why that makes sense. If you have, this is the bottom half and this is the top half, if your bottom card stays on the bottom, then when you weave them together, your top card stays on the top. But if this doesn't make sense to you, you can just use this formula. So for 52, well, 2 times, so we want to use this case because we're greater than 26. And 2 times 52 is 104, minus 52 is 52. So that's the only place that one will ever go. Okay, now we need to think about all the other positions. There's 50 more to consider. So let's look at when we start at 2. All right, so to find out the next position that 2 is going to go, it satisfies this condition. So 2 times 2 minus 1 is 3. So the next spot it's going to live in is 3. Okay, and then we just keep this up until we get back to 2, and that will complete our cycle. So 2 times 3 is 6, minus 1 is 5. 2 times 5 is 10, minus 1 is 9. 2 times 9 is 18, minus 1 is 17. 2 times 17 is 34, minus 1 is 33. But don't get too complacent just plugging in over and over, because notice, now I've dipped into the top half of the deck. So in the first 1, 2, 3, 4 permutations, that card in position 2 is going to stay in the bottom half. But after the 5th permutation, it's going to move to the top half. And that means that I'm going to have to apply this rule to determine where it's going to go next. Or just sort of numerically, because this number now is greater than 26. So now I want to do 2 times 33, which is 66, minus 52, which is going to be 14. And now jump back down to the bottom half again. So now I use this. So 2 times 14 is 28, minus 1 is 27. Okay. And then 27 times 2 is, so I need this case. So 27 times 2 is 54, minus 52 is 2. So I don't need to write that 2 again because we just bring it back around. And remember, the rule for this notation is that this position goes here, this position goes here, etc. And then here you just wrap around to the front. Good. So take a look at this, this permutation here. This thing has order 8. It has 1, 2, 3, 4, 5, 6, 7, 8 things in it. So that's probably good news. But we need to check the rest of them. So rather than painstakingly writing them out, let's just do this. There they all are, like magic. Okay, so we can, just by inspection, discover that these are all of order 8, except for one. This guy is mysteriously of order 2, and it's kind of interesting. But you just get this directly out of this, these rules. So for 18, it's less than 26, so 2 times 18 is 36, minus 1 is 35, so you get this 35, and then you plug 35 in. 2 times 35 is 70, minus 52 is 18. So this cycle has order 2, and this is really interesting, and when we get to the cards, I'm gonna point this one out. But for the rest of these things, all of these cycles have order 8, which tells us then exactly the result that we were counting on, that if we perform the perfect Faro, or perform this permutation on a deck of cards exactly 8 times, because that's the least common multiple of all of these cycles. So the orders of the cycles are 1, 8, or 2. The least common multiple of those numbers is 8. So 8 is a multiple of all of those numbers. So if we do it 8 times, we're going to get back to the original order, which is pretty nice. So let's go ahead and do 8 perfect Faros. So here we are in new deck order, and we're going to go ahead and number them. We're going to let the ace of spades be position 1 and number them right to left, I guess. But this has the nice feature that the spades enumerate their original positions. So you can see that at least till 10, they're just indicating exactly what their position is. I've also written down the cycles over here. And so as promised, I said I would point out what was going on with this order 2 cycle. So you can check position 18 is going to be the 5 of diamonds, and then position 33 is going to be the 5 of clubs. So if you keep an eye on those two, and I'll try to point them out as we proceed, they will just alternate positions, whereas everything else, except for the top and bottom, which will remain fixed, of course, are kind of on this, well, order 8 cycle. So what I'm going to do is follow the journey of the 2 of spades. Now, I could have picked any of these, really, but this cycle should tell me exactly where I'm going to find the 2 of spades after each iteration of this permutation. So let's get started. And remember that it's important that we make sure that the ace of spades is, in fact, remains on the bottom or in position 1. All right, so there's our first Faro, and let's square them up. That's my favorite part. So now, well, this is kind of interesting. So notice that in the new deck order, we alternated blocks of red and black, and so once we weave them together, we get the reds and blacks separated. You can also observe what I mentioned in the 8-card example, that the relative order of the top and the bottom is maintained. So if you look at every other card, we have ace, 2, 3, 4, etc., and vice versa for the top, ace, 2, 3, 4, etc. So these are just kind of nice observations. But in particular, we said we were going to look at the journey of the 2 of spades. So after it starts in its original position, it should be at 3, which 1, 2, 3 it is. And I also said keep an eye on that, what would we say, the 5 of clubs and the 5 of diamonds, which should just be switching places, which so far they have. So that's so far so good. All right, so that was our first of 8. Let's keep this going. Okay, so there's number 2. And we should now, let's take a look. So our cycle tells us that now the 2 should have moved to position 5, which 1, 2, 3, 4, 5 is the location of our 2 of spades. So that looks good so far. And notice the numbers are starting, the values are starting to pair up, and we have a really nice symmetry, which is not a coincidence, though it is based entirely on the original ordering of the deck, that we had them ascending and then descending is what gives us this. So let's do another one. Okay, and in case you didn't see it before, let's see if we can get this into focus. Remember, it's important that you do weave them exactly 1 and 1. So once we've done this third one, the next location for our ace of spades should be position 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. And again, I didn't spread these very evenly, but again, I told you to keep an eye on that order 2 cycle. So there's that 5 of club and 5 diamonds jumping back and forth again. And I'm not counting to 18 and 35 every single time, but you can if you'd like to pause it and check that that's going to work. All right, so here's our next one. Okay. All right, so this is a much bigger jump for the 2 of spades. So let's see where it is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, which is where we said it should be. And notice it is still, in fact, in the bottom half of the deck. And this is the last iteration, which will stay there because our next position is going to be 33, according to this. So let's check it out. Okay. All right, so now the 2 of spades should be in position 33, and the cards seem very mixed at this point. And this sort of intuitively should seem reasonable because we're right in the middle of our cycle. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, there's halfway, 27, 28, 29, 30, 31, 32, 33. So there's that 2 of spades in position 33. So that's good. All right, and that also told us where 26 would happen, or 27, I suppose. All right, so we've got a few more of these. And now we know the next one should bring our 2 of spades to position 14, so it's going to bring it back to the bottom half of the deck. So that's good. Less counting. All right, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so there's the 2 spades, and 14 where we predicted, and we can see now even that we're starting to restore a little bit of order, that we're starting to get clumps of the same suits near each other. So that's probably going to bode well for getting back to the original order. All right, so let's do another one of these. Up next, we should find our 2 spades in position 27. So let's check that. And let's talk about why that makes sense. So now things are really starting to get back in order. And it's in position 27, which I'm not going to count to this time, but observe that this is exactly halfway. So this is position 26. And that should make sense because we're going to need it to go back to position 2. So what we see when we split these in 2, notice that not only do we have clumps of the same suit, but they're all separated by 2. So once we perform our final Faro, we should get the missing things back in between them. So that 2 of spades at position 27 is now our halfway point. So let's do one more of these guys. All right. And now, should once again, there we are, new deck order. That 2 of spades is back to position 2, as is everything else, including our order 2 thing, because we did an even number of permutations. So that 5 of diamonds, 5 of clubs are where they're supposed to be, and everything's there. So I just want to say thanks for watching. I hope you learned a little bit about permutations, which are part of a broader branch of mathematics called combinatorics. And I hope you were impressed by my 8 perfect pharaohs. Tune in 2 weeks for another magic video. Thanks again.